Yep. Okay.
Go right ahead, please.
Okay. Hi, Will Sobel. I'm from VIMANA, and we develop industrial analytics AI platform for discrete manufacturing, or kind of a deep vertical platform. What I'm going to talk to you today about is so you want to hire a data scientist. You want to get into predictive and prescriptive, and you've built yourself a nice data lake. You filled it with stuff, and you think you got a swamp. And you want to do amazing things with that, but how do you enable your data scientists? How do you get your data scientists to the point where they can actually start to derive valuable insights from this thing that you've built? And what are the steps that you can do to avoid creating a data swamp in the first place? So let's talk a little bit about just what type of analytics. This is even like before you go and hire somebody like a data scientist, they're very expensive. What are you trying to do? So there's four basic types of analytics. If you think about it, there's descriptive, which are sort of your KPIs, backward looking. Those are things like OEE, reporting, just what happened, telling you what happened in the environment. Then you get into the diagnostics. Diagnostics tell you why it happened. This is some of your root cause analytics, supply chain capacity, et cetera. To do the first two, you don't really need cloud platform. You don't really need to have any fancy stats. You can do this with pretty standard technologies. It's really when you start getting into the predictive, when will it happen? So you're starting to look forward into that time horizon. You're starting to collect data in real time, and you're starting to then predict when something is going to happen in your plant, such as predictive maintenance or even dynamic scheduling. You want to be able to move things around to the best machine based on the capabilities at that point in time, or dynamically optimize your processes based on what's currently happening out in your shop floor. Those are predictive. You need to have deeper, more rich analytics. You need to start doing cloud. You need to start having on-demand compute resources. And if you want to even go to the next level, which is basically prescriptive, which is how can I avoid problems in the future? How can I consistently improve my processes? Do what like Vijay was talking about, which is like closed loop engineering, where I get data from my machines and then I can make prescriptive changes to the design for manufacturing and engineering, so that when I go out there, I will not have problems in the first place. So that's where prescriptive is kind of the apex and we're trying to get to. And for that, again, you need to have your data science team and your cloud-based platform, because you need that level of compute and storage to handle the terabytes or even probably petabytes of data that you're going to be collecting. So I don't know if anybody's seen this. This is actually a study that was done by Google. It's interesting. It's called the Hidden Technical Debt of Machine Learning. When you're looking at a machine learning platform, just so you're aware, each one of these boxes indicates the size, the relative size and complexity of the code that's written to be able to support machine learning. So the first thing is configuration, basically all the machines and all the metadata and everything else around this thing, as well as the configuration of the platform itself, the data collection platform you have. So this is MT Connect, OPC UA, these types of standards to be able to get your normalized data coming in, but all that machinery to be able to bring data into your cloud. And then you get into feature extraction. This is classifications and the ability to be able to do multidimensional analysis and KPIs and such. Verification, data has to be correct. Resource management, basically being able to dynamically spin up and spin down machines. And then you need to have your data scientists have their analytical tools like R, Python, TensorFlow, et cetera, to be able to do it. And you need to be able to provision all those. So this is your serving infrastructure, to be able to manage that data, get it to where it needs to be able to then run your analytics. And if you want to put this into production, you need to have monitoring and process management to run your batches in near real time, as well as cycle the models out to where they need to go. This is all to be able to enable this, which is basically your machine learning code. That little box in the middle is what we talk about a lot. Those are your insights. That's the code that's actually written like in R to be able to execute that model. So often we build these, you need a huge amount of support and buttressing to be able to get the type of insights that we're talking about. So just to be aware, when you enter into this road of predictive analytics and you're going to get a data scientist and you want to enable that person, you're going to need a lot of stuff around it. And there's some good platforms out there from many different vendors that support a lot of this infrastructure, but just be aware that you need the infrastructure. Don't try to go into it without this. How do you get started? So everybody's been talking about this week. It's great. Business objectives. Start with a business objective. Don't start with a bunch of technology and think, oh, I'll come up with a business objective later. Because if you do that, you probably won't get results. The idea is you have to start with, okay, what is my end goal? How am I going to achieve value? And then back out. What are my data sources? Where am I going to get the data? What type of data do I need to be able to get these insights? Do I need just simple state-based data, or do I need things like load speeds, feeds, telemetry, and all kinds of other things from the machines to be able to actually get any value? Then you need to have a bit data preparation. So this is where you start to what we call data enrichment. This is where you start to classify certain periods of time and give context to that data that you've collected, so that then you can start doing your analytics. I'll go much deeper into that. You then get into your descriptive and diagnostic data, which is basically getting your KPIs, and this is what we're talking about, those first two boxes, to start getting your KPIs and your metrics, which also help, again, start to contextualize the data. And then you can start getting into your industrial AI. This is where you start actually mining that data, creating the models, doing the clustering and the predictive and the machine learning. If you get to either deep learning or Bayesian, whatever processes, basically those steps you need to go through to be able to get to this final step of being able to do your real deep analytics. As part of this flow, you're getting all this data from machines. So I'm also a standards guy. I do the MT Connect standard. I'm working with the OPC Foundation to work on the OPC MT Connect companion specification. When you start collecting data, make sure you do it in a standardized way. This is a very important point, because if you try to go and create your own dictionaries, your own ontologies, your own protocols, your own ways of representing the data, you're going to be in a world of pain. And it's going to be a big, heavy lifting job, and it's really not something that you need to do. There are standards out there, MT Connect for machine tool and discrete, you have PackML for packaging equipment. OPC UA is a great foundation for being able to represent that data and carry the data, providing a syntax and a grammar to represent it. Then you can get into your process analytics and your prognostics. The idea is to be able to do this so it scales across thousands of machines. So you have tens of thousands of machines. So when you use standards, the nice thing is, if the machines start coming out with the standards already installed on the machine, you have zero work to do to connect up that machine. You have zero work to do to be able to understand what the data means coming off that machine. With semantics, you get the benefit that you understand the meaning of the data right out of the machine. With common standards like OPC UA, you have a way to be able to understand that information model, the structure of the information model, using standard technology as well. We consider this as a data source. This is actually taken from one of the many data sources that we get. Basically, what we've done is doing a clustering based on the native information that we're getting from the machine. These are all similar machines, lathes, mills, mill turns, and such. What we found is that the native machines tend to have their own special way of classifying everything and calling everything. What you need to do is normalize it, because when you want to start analyzing data, what you want is to be able to compare like things to each other. So if you have a standard, ontology or information model that you can use to be able to represent that data, you can then look at it as similar or the same set of information from every single vendor that you have out there. And that's how you scale. That's how you make it work across all the different vendors of equipment, is you have to have this normalization up front of the semantics and the meaning of your data. And then you get into the phase of what we call data preparation, which we talked about. This is where you start contextualizing the data. This is also another very important point. Then we have some speeds from a spindle. What we want to do is we need to actually combine that with various different states of the machine. These are ready and active states. You need to start building these duration-based events. Basically, these are things that are occurring, but they're not just a point-in-time event. These are events that actually have a time dimension associated with it. Because what that allows you to do is then to add, when is the machine actually doing work? Well, when the spindle is spinning and when the machine is active, when it's actively running a program. Now we know when things are actually happening. So now we've got a little bit more insight. We can start analyzing the actual spindle time of that machine for predictive maintenance or for process analytics or something else. Now we can even look at it more. We can look at, okay, what program was running when that machine was running, when that part was being made. And we can start digging down a little bit deeper. And these are, again, more intervals. So what we're doing is what's called sort of interval calculus. We're being able to then allow the data scientists to join all these intervals together to be able to get a picture of exactly what's happened. We want to say, okay, when is the machine in the cut, producing material in the cut, when the load is over a certain percentage, when the program is running, when a tool is loading, when so forth. Now we can focus right on that interval. We want to be able to do that same thing across 100,000 parts that were made on this machine. We want to be able to do that across 100 different vendors of machines that are making the same part. We want to have the same semantics across all of that data, incoming data, as well as the analyzed data. So we're classifying everything the same way. We need this homogenization. And that's what's going to enable your data scientists to then be able to start mapping out the signal that will then feed into the learning models. An example, so I'm going to go through a quick study here. This is a bunch of load data. As you can see, it's very easily interpretable. And we've mixed it with the, this is actually from a grinding machine. These are the different machine operational states. And what we were able to do then is we're able to now focus in on this mess and look at the exact signature of each one of these parts as it's being ground. So by sort of intersecting this real-time data with the process data, we're able to get that. The next thing is, we want to find anomalies. So we're going to train our set. So again, we've now narrowed it down. We've been able to clean the data up by being able to, again, take these interval associations and contextualize the data. And what we want to do is identify this master part. What is a good part? What does a good part look like as far as that load signal? And what does it look like on all the different axes? So this is a multivariate problem. We have, spindle, x-axis, y-axis, and we have basically the grinding wheel, the spinning speed. We also have parts that are being made. We have to be able to identify dressing cycles, a lot of different things. So what we need to do is right now just focus on what is a good part of a certain type of part, and then be able to get that signature across all these different axes and across all the sensor data that we're bringing in. And here's an example. So we find a master part. This is what a good part looks like. Now we find parts that don't match. So if we get anomalous data like this, we can now start to identify well, first off, we'll build a model so we can identify bad parts and start to get classifiers. Then we can push that model down, and as the process is executing, we can stop that process before anything goes wrong. So we can actually start getting predictive about it in process. Next step is we become prescriptive about it. We start to feed that information back to the engineering group so they can start to create programs and start to prescribe what's happening, what should happen. So what are the correct process parameters? How are people running these good parts and bad parts? What is the difference? Why is this happening? And then how do we correct it? And how do we find solutions so that this will never happen again, so we start getting less bad parts? The other thing that's interesting, I'm going back to like what Vijay was talking about with tooling, one of the things that we found, there was a huge variation. So this case study that we were doing, they were making, some operators were getting like 100 parts on a wheel, some were getting 1,000 parts on a wheel, with various different numbers of good and bad parts. And they were saying, why was this happening? Why were we getting so much variance? And this was the study that we did, and we found a lot of issues. I mean, one of them was, cutting wheel quality. If you have multiple vendors of cutting wheels, you're buying from multiple different vendors, maybe you think you're getting a cheaper price point on this one vendor because they're selling you a cheaper wheel. But what really comes out is that you're not getting as many good parts, and it's wearing out faster, and it's causing a lot of problems. Without the data and analytics, you may not know that. You may think, oh, we're saving a lot of money here because of our consumables. But really, you're losing money. You're losing money on parts and productivity. So by being able to identify what a good part looks like, what a bad part looks like, and then push those analytics down, become prescriptive, look through your sourcing systems and your various other engineering systems, and also being able to track exactly how that operator is running that program. We're then able to target exactly why this thing is going wrong, how to fix it, how to prescriptively change it so it doesn't happen in the future. And we provide this using, our data scientists, or we have a bunch of data scientists in our company. We provide them these workbenches where they're able to do all of these queries and basically do the intersections and be able to compare commonality, basically being able to do these slices across multiple instances of the same part, and then be able to do the comparisons, and then build the model. So we build learning models and training sets off of this, and then we can train the sets and then build, ship those models out there. So to wrap up, first off, you need to start asking questions of your platform providers. And first off, start off with business objectives that you want to achieve and you think are achievable. And identify your information sources. Make sure that they can connect up with the information sources. They know how to deal with sensors. They know how to deal with the type of machinery that you're connecting with. And you can get rich enough data. And I would also say that they're using standards, because if you decide that you want to, bring somebody else into the fold, like Vijay was talking about, it's going to be ecosystem. It's going to be a lot of different players. You want to make it so that that data set that you're collecting in your cloud can be used by not just one company, but can be used by multiple companies. So you want to be able to make sure that you have standardized information models. They're well documented, and all the terminology, all of the terms and units and vocabulary is well designed, well documented, and is also provided by an open community, so that when you bring in the other vendor, basically they can just hook up with it. They already know it. You're done. So that gives you a huge leverage when you're working with information sources. And that's where open standards comes in. Like, MTConnect and OPC UA provide that foundation of the information model and then the semantics on top of it. So if you start out with that type of information, you put that into your data lake, chances are you won't get into a swamp. It will be usable, extensible, as well as being able to allow you to bring other parties in to give you value. Make sure your system is trustworthy, you have adequate security. We're talking a lot about that at this show. So, it's beyond just, security. It's also resilience and fault tolerance and things along that line. You got to consider those. What happens when a machine goes down? Do I still have the analytics running where they need to be able to give me my latency and my determinism to be able to affect processes as they're in process? And then pick knowledgeable partners who have done things like this and know how to work with the type of data that you're currently wanting to analyze. And that's...
Well, thank you very much, Will.
I think.
That was great.
Thanks.